All right, good afternoon everyone and welcome to another Compass Wednesday, and thank you all for showing up. We have a full house for Roland's talk today. There was actually a suggestion in our Compass Committee student emails this morning that maybe the whole committee should introduce him, since this is Roland's first talk in 8 years, but I get the honor today as one of the OCE students. Roland's presentation today is part of our special ATM and OCE faculty presentation series. As part of this talk, he'll give us a lot of his background and history in his work, so I'll be brief with my introduction. As a scientist, Roland is an outlier in a family of 3 generations of architects, instead getting his degrees in physics and geosciences. 15 years after completing his PhD, Roland joined the Rosenstiel School as an associate professor in 2008. He got tenure in 2014, and he's been a full professor since 2019. In addition to being a professor, Roland has been the MPS Applied Remote Sensing track leader since 2016, the graduate program director for ocean sciences since 2018. He has also been a school council member for both AMP and OCE, and was the speaker of the school council from 2022 to 2025. Roland is also the backbone of Compass, organizing our talks, keeping the student committee in line, and most importantly, bringing our coffee and snacks. So without further ado, let's welcome Roland to talk about SAR remote sensing of the ocean.
Yes, okay, thank you for the nice introduction. Thank you all for coming. Some of you knew I said if nobody shows up to my own talk, I will quit organizing the seminars, so that will not happen now. That's very good. And so yes, I want to talk a little bit about SAR in general and some steps of my career, as we do in this special presentation series, and then show you some latest results from our recent projects. Now this thing doesn't want to advance. There it is. Okay, so SAR started as early, spaceborne SAR as early as 1964. That was unclassified just 10 years ago or so. That the Americans already had the first SAR satellite from December 64 to January 65, and as you can see there, it took some usable images of some land scene there on the left and some coastal scene on the right, where you even see signatures of waves. And this was quite an adventure in 1964. They had a system to downlink the raw data to process them on the ground. They took images only over the US because they didn't want the Russians to see what they were able to do. And then they had a film to record the raw data on the film. Those were not processed images, just raw data for the SAR. And then when the mission was over after 3 weeks, they didn't have solar panels and such things. They had only a battery on board. And so after 3 weeks it was over, and they sent a film with these collected raw data down with a parachute, and then there was another way to process the images. Quite crazy. So that was in 1964 already. And nobody really knew much about this until not long ago. So synthetic aperture radar. What is it? It looks can look like this. This is a satellite Envisat there with a long antenna. I forgot to take my laser pointer, but I can use this. So there are many things on Envisat, but this is the SAR antenna here. This is a solar panel, and there are some other instruments there. This was the biggest one with the SAR, and so in general, the SAR is a high-resolution imaging radar. It requires platform motion to synthesize a long antenna. You need a really long antenna of a mile or so to get a really high resolution to make a narrow beam. That's not possible, and the SAR can use a shorter antenna, 10 meters in this case, or maybe 12 meters on Envisat, and it adds the data together in in an advanced, sophisticated way while it flies along and synthesizes a long antenna. So instead of having a physical long antenna, you record data over some time and process them in a way as if they were recorded by a long distributed antenna at once. So spatial resolutions typically are on the order of meters. Latest ones can be less than meters. Swath width, how wide the image is, can be up to 500 kilometers. The SAR looks through the clouds, so it's independent of daylight and clouds. And ocean images show surface roughness variations. And here are some really old examples. This is all from an old presentation. This is somewhere southern end of Italy. You see the mountains there, and you see the atmospheric signatures there over the ocean that looks like clouds, but those are convection cells in the atmosphere that make surface imprints where the surface roughness is increased. That's what you see in the SAR image. Here's another very old example from ERS-1. At the Strait of Gibraltar, you see internal waves there on the right, which are waves between layers in the ocean. Of course, you know that, and what they do at the surface is that they modulate the surface roughness, and then you see these patterns. And there's also a black line here, that's a surface slick there. That's oil released by some ship. So all we see is from the surface, but there are connections to things under the surface and also things above the surface. Another example here, some river plume with the front. And this is interesting here. This looks as if you can see the bottom. This is somewhere at the coast of China. So this is all covered with water. The reason why you see the bottom is that there is a strong tidal flow that gets modulated by the changing depths. And then you have current gradients that modulate the surface roughness, and it looks like this. And this was actually one of my main topics as a PhD student, to figure out how we can make a better model to describe and maybe invert these signatures to retrieve the depths from the radar images. A little list of missions here to give you an impression. So Quill, that first one there was in 1964. Then the first really well-known one was CSAT in 1978. It lived only for 3 months and it failed. It was supposed to live longer in that case, but it didn't. Then there were some shuttle missions in the 1980s, and only in 1990 we got the first one that really lasted a little longer. ERS-1 lasted quite long actually, and there were some more. Japanese one. Space shuttle missions, there's the SAR here. The Europeans launched ERS-2 after ERS-1. The Canadians launched satellites, and then in the 2000s there were even more additional countries came into the game and launched more and more SAR satellites. Again, newer versions, newer generations in the 2010s. And then around 2020, some commercial companies came into the business with new, cheap, small satellites, but many of them. And you will see they are quite capable of taking nice images. They cannot take as many images and not as large images as the older, bigger satellites, but they can take many images and very quickly. If you need an image somewhere, you can program them to take an image very soon, because there are so many of these satellites around. And I estimate that we have about 100 SAR satellites operational right now from all these, mostly from these commercial constellations. So a little technological progress here. So this NVSAT, which was the biggest one, launched in 2002, they always said it's like a school bus, more than 8 tons. Total mission cost was 2.5 billion euros over about 10 years, plus construction time. It had 9 remote sensing instruments. That was the idea at the time, to have many instruments, but they didn't really work together well. And then the next generations were more focused on single instruments, like the Sentinel-1 series of ESA, which is like the successor of NVSAT. Still weighs 2.3 tons. And there was TerraSAR X at X-band, which is easier to make smaller because all the components can be smaller at X-band compared to C-band. Still a little more than a ton. And here, this latest microsatellite technology here of SAR in Finland enabled them to make a SAR satellite of only 70 kilograms. And since 2018, they have already launched more than 60 of these little satellites. Now, how good are they? Maybe they are not good, right, when they are so small. But here's an example image. They can do amazing things with these satellites. As I said before, these satellites cannot take as many images and not cover such large areas as the Sentinel-1s. They will probably not last very long per satellite, but it's much cheaper to launch the next one, and they have 60 approximately now. They will launch a few more this year, and they will keep going with better and better and more satellites, and you can get a lot of images wherever you want in really good quality. Now a little bit about my career. So I started to study physics in 1985 at the University of Bremen, and in 1986, I started to take a theoretical physics course with Werner Alpers. And I see he is here. There you see him, still alive. He was 50 years old in 1986, and this year he will turn 90 years old. And so, what is he doing something? Hello, Werner, we can see you. And so in 1988, I started to do my master's project with him, and I finished it in 1990, and continued to work with Werner Alpers then at the University of Hamburg as a PhD student. And here is a paper from my master thesis results. This was published in 1993, a comparison of wave heights from the GeoSat altimeter and a wave forecasting model. That's what I did for the master's degree. Then in 1993, I got my doctorate degree, stayed with Werner Alpers as a project scientist. Here are some papers coming out of my dissertation about modulation transfer functions and this modeling of the radar imaging mechanism of underwater bottom topography mostly. And then in 1998 to 1999, I had a fellowship to work with Don Thompson at the Johns Hopkins Applied Physics Laboratory in Maryland for a year, and we worked on a long track interferometry. Published this paper together about a numerical study, still based on my numerical imaging model that I had developed. And then after coming back from there, I got a kind of tenured permanent position in Hamburg, but only as a scientist who had to do what the professor, who was the boss, told him. The boss was not Werner Alpers anymore. So it was at least after 2002 or so, became a little less pleasant, and there was some pressure to leave, and then I went here to Miami in 2008. Little more about this model that I developed. So it looks like this. It uses all kinds of inputs and simulates all kinds of things, and as the output it can simulate a SAR image that looks like a real SAR image with all the noise and all the imperfections, all the distortions that you have. And so you can give it the specifications of different types of radar systems and see with these simulated images what those radar systems would be able to do, existing systems or proposed future systems. So this so on one hand we need this to interpret existing images correctly, but also for theoretical studies on desirable future developments, and to evaluate some proposed instruments. So that's what we did with that model. That was most of the stuff I did in Germany, really, during the first 10 years or so. My main work topics here on this slide, so analytical and numerical modeling of the SAR signatures, again with that model there. I worked on wave, wind, current, and water depth retrievals. Then a long track interferometry came into the picture a little later. And we did studies on capabilities on future instruments. We developed algorithms, especially here in Miami, to correct SAR images for imaging artifacts and for statistical inhomogeneities. And the latest project is about land topography and hurricane damages. I will show a little more about that at the end of the presentation. Now, who were the most important people who supported me. Werner Alpers, obviously, here's a picture from after my PhD defense in 1993. I have changed a little more than Werner Alpers if you compare that with the Zoom picture there. There was also Klaus Hasselmann involved in this. So this whole idea of comparing the wave heights for my master's thesis project there, that was from Klaus Hasselmann. And he also, his ideas were the fundamental ideas for this project that I did for my PhD later, this model development for the radar imaging, the fundamental equations had already been written down by him, but some student who had tried to put that into a computer to do some simulations had not succeeded, that didn't work. So Werner Alpers asked me to see if I can make sense of Hasselmann's theoretical ideas. And Hasselmann, of course, got the Nobel Prize in 2021. There he is with his medal. Unfortunately, I didn't publish any papers with him as a co-author, of course, from today's perspective. That would have been a good thing to do. Then there was Don Thompson, my host in Maryland at Johns Hopkins, who also helped me to come to Miami. Unfortunately, he died, surprisingly, around 70 years old, I think, at 69 or so, 2011 or 2012. He had a heart attack. He was really a strong supporter. Then a really important guy who is still alive and still helping me sometimes, Hartmut Runge, an engineer at the German Aerospace Center. He always had some interesting ideas for experiments that we could do with the German instruments on the space shuttle and later on the satellites. He helped me to get some data that I didn't even know existed, but he had somehow some connections there to make people acquire some special data, and then he knew that I would be able to process the data. So we did some really interesting things together. And then, of course, Hans Graeber, who helped me to come to Miami, and we are still working together very much and sharing students and so on. The list of students should not be missing here. So I had some students in Germany, then I had Fernando Montero, and my first PhD student in Miami was Connor Smith, who actually was here a few months ago visiting us. He now has a little company doing some services still related to remote sensing and data analysis and measurements. Then we had Lisa Nyman here in 2019, who is now a high school teacher or something like that. Sam Frodney was the third PhD student who finished in 2023. She is now at Johns Hopkins APA. And now, currently, I have Victoria Pizzini, who is sitting there, and Katja Childs, who I think is not sitting here. And we also have many students here together with Hans, who were formerly Hans' students, but I work with them, like Gabi, I see there's maybe some others in the room. So Maddie and Gabi and Katie are still here. Katie is also sitting somewhere. There she is. That's the team right now here, the bold people. And then there are a bunch of MPS students here and the years when they finished. And currently we have 3 still in the team here. Suteng Fang, Hannah Heath, where is she? There in the front. And Katerina there. So they are my current students. I've never had lots of students, but I have had pretty good students, I would say. Okay, now we come to the topic of a long track interferometry. What is that? That was really the next topic after developing this fundamental model. And I still worked on it when I came to Miami. So the long track INSAR uses 2 antennas to take 2 images with a short time lag. And that can be exploited to measure Doppler shifts and line of sight velocities and current fields. And it was originally on this DC-8 of NASA sometime in the late 1980s. And then we did experiments in Germany with this system here with 2 antennas. And then we had it on the space shuttle. This space shuttle mission was mostly for topographic measurements, but my friend Roland Romeiser realized that this could also be used for a long track interferometry, and we did get some very exciting results from that. And then we had TerraSAR X, which has another experimental capability that only Hartmut saw that this was possible with the hardware. The satellite was not really designed for it, but he convinced some friends within the German Aerospace Center to do these experiments for us so we could test current measurements from space. Here is something from the SAR SRTM on the space shuttle. Here the current field in line of sight direction at the Dutch coast, so there's only one component shown in color. This was in early 2000, and I had friends in the Netherlands who had a model, a circulation model for this area, and they didn't have a dedicated model run for exactly this time, but they had a current field for the same tidal cycle that they sent to me for comparison, long after I had finished the processing of this. And this is their current field, just the line of sight component. You see that they agree quite well. And the reason why the current looks like this is the bottom topography here. That this was the input to the circulation model. So you see that we measured this quite well from the space shuttle, and good quantitative agreement, 0.1 meter per second, at 1 kilometer resolution, and that was more or less what we had predicted before. We had already done some simulations to see if this would even make sense to do this kind of measurement, and I think the data already existed, but before I agreed to take this data set from Roland Romeiser and do my tests with it, I did some calculations there at the end. So this was quite good. We published it in Transactions on Geoscience and Remote Sensing, and this was so exciting that it made it onto the front page of that issue of the journal. This was the first example of current measurements by a long track INSAR from space. Then we had Tandem X, which was a second TerraSAR X type satellite flying in close formation with the first one for the purpose of getting a global digital elevation model. And this diagram here shows, so they are circulating around each other while they are orbiting the Earth. So one side of the Earth, one is on top of the other, and on the opposite side the other is on top. And altogether they have the same orbital period and just pass each other twice on each orbit. And then most of the time you can use them for topographic measurements. And at some places you can use them for current measurements. Again, Roland Romeiser's idea, of course, because he knew these things and he knew when there would be special opportunities to do it. And we had a paper here where we were able to compare, let's begin with this, compare the regular capabilities of TerraSAR X with the divider antenna and Tandem X in a perfect distance between the two satellites, which was theoretically much better than having just a divider antenna. This is somewhere north of Scotland, so-called Pentland Firth, where there's a strong tidal current. What you get from the standard TerraSAR X divider antenna product looks like this, very noisy. You have to smooth it a lot and you get a surface current, but at a low resolution. Compared to that here from Tandem X, we got this. This is without smoothing. You see, if you look closely, you cannot see it very here, but you can see wave patterns there. You really can resolve the orbital motions of the waves in that area. So this was much better. Of course, we did some more statistics and showed how good it really was. So if you want perfect velocity measurements from space, it can be done. The system could be built. It doesn't have to be on two satellites, but of course you need people who want this and to propose it. And so far we have not succeeded. There was a proposal for something similar to this that would even measure vector currents, and was selected by ESA for some kind of further investigations, but in the end it was not selected for a satellite mission. Maybe in the future someone else will succeed with that. So here if you compare again what we have without smoothing in the image from the divider antenna and from Tandem X is much better. Now we shift gears again, we come to the topic of filtering images and improving the data quality. This is a long track INSAR data set from the Columbia River mouth from one of our projects, from the divided antenna mode, I believe. And you see these ghost signatures, right? You see, so here is this thing coming out, this, how is that called? Breakwater jetty. So you see a ghost signature of it here, you see some other things, and here in this face image you see it even more, that things are visible 3 times. You would want to use this here for current retrievals, but that was not possible with this original image that we obtained this way from standard processing. And so I developed a filter to improve that. And so the explanation why these ghost signatures happen is you look at something like a sailboat there, you think your antenna beam is going there, but the antenna has side lobes like that. And if there are some strong scatterers on the 2 sides, on land or in the water, but the worst ones are the ones on land, close to the water. They can be really bright, and there are some metal structures. You see ghost signatures of them over the water because the processor cannot discriminate between the side lobe signals and the main signal. And what you can do, you can reduce the bandwidth of your processor to look only at the place where the sailboat is, and then the corresponding ghost signatures in this case would be from places where there is no house and no tower. But then you lose, so then you don't have those ghost signatures anymore, but you lose data quality because you are not using your full processing bandwidth. And I developed a technique that would somehow make so it would reduce the bandwidth of the image first to reduce the ghost signatures. That can be done. You see how that works, and with less and less bandwidth, you get less and less ghost signatures, but you also get a noisy image. And the idea was that if you have this narrow bandwidth window, but you shift it from left to right through the whole available bandwidth, and you make a set of images, so-called sub-aperture images for the different parts of the spectrum. Then you get a series of images like this, where you can see the ghost signatures appearing and disappearing. And now if you pick the right ones that don't have ghost signatures at the different places where you don't want ghost signatures, you can combine several of them without ghost signatures to get a better averaging and a less noisy image than if you just take one image in the center with a very narrow bandwidth. And so did you see that? So this was a single sub-aperture image that a simple algorithm would give you by just reducing the bandwidth very much. And if you average over multiple such images, you get a nicer looking, less noisy image, still without ghost signatures. So it's a little, not much time here to explain this in detail, but I guess you get the message here that this is a little tricky. You need to understand well what the radar is doing and how to process the data and how to filter the data. And it's not just going into Photoshop and applying some simple filter. You need to know what's going on and why these signatures occur and how you can process the data in a better way. Here again, the input product, and then after the filtering, you got this. No ghost signatures of that jetty anymore, and our phase image would now be usable to retrieve currents. Then, after learning how to do the spotlight reprocessing, we looked at some other examples, like this one here from the California coast, which has waves in it. This is not a long track INSAR now, this is just a single intensity image, but with a very high resolution, theoretically just 0.17 meter in this direction here. So the SAR in this case has looked at the spot for 6.72 seconds. And the problem with that, when you do it over land, you get a very nice image here, right? High resolution, almost no noise, not so visible here, but that's how it is. That's why they invented this mode, to get a very high resolution over land. Over the ocean, when you look for 7 seconds, the image gets blurry because the waves are moving too much. So here this is not too useful as a standard product, but after learning, this illustrates quickly what the SAR is doing, what the spotlight SAR is doing. This is the regular mode of operation, just looking to the side, achieving a resolution of a few meters. And in the spotlight mode, so how can it look at the spot for a longer time? It steers the beam and it makes only a small image, but it looks at it for a long time, and then you have more data. You can synthesize a longer antenna of that little spot and get a very high resolution product like this. So anyway, it's blurry, but not very useful, and we can reduce the processing bandwidth and get an actually better image with better wave signatures. You see, it looks more focused. And we can again do a set of sub-aperture images now, sliding our window over the spectrum, just for a different purpose now, because this also represents different time steps during the 7 seconds. And if you look closely, you see the wave motions. This window here, still 7 seconds is not so much, but if you look carefully, you see a little motion there. If you zoom in, you see it even more. See, you see the waves moving, and you still see a lot of noise. And now I wanted to go a little quickly through all of this. This was another complicated filter procedure, but you can apply some Fourier transforms and do some spectral analysis with the frequencies you get from the changes between the images, and you know how fast ocean waves should move according to the dispersion relation for ocean waves. And you can filter out everything that does not move like ocean waves. And then you, after filtering everything out that's not like ocean waves, you can do an inverse Fourier transform and get back into the space domain. And here's the result. There were maybe 5 slides in between that I cut out that explain the process in more detail. But you can see what we have now. We still have the same wave patterns there, but without all the noise that's from speckle noise and nonlinearities and other features that were there. And so this was used further for wave retrievals. You can use this for a new way of retrieving wave spectra. I will skip over that again because I don't have enough time. But we will look at this application here, bathymetry retrieval. This is an older image here from a time here from 2009, an early TerraSAR X image from a time where we didn't know that we could do this, but we still had the data. And I said, let's try. This is only 1.2 seconds. So the motions are even less obvious here, but there are motions. And so again, spectral analysis now in small windows, so we could analyze the waves individually and see how they change within the image because of the changing water depth. You see some refraction patterns here, right? So there is a changing depth, it's getting shallower towards the coast, obviously. And so what can we do with that? We do the wave analysis and we fit a water depth to each local dispersion relation, and we get an estimated water depth. This shows some energy distribution here over the dispersion relations for different depths. Anyway, after applying the filter, we got these depths, and they were consistent, not too far away from the known depth map of the area. And then, of course, you have now separated your physically meaningful wave patterns from the noise, and you can go back with the inverse Fourier transform and see nice wave patterns. You still don't see them moving, but since this is all in Fourier space now, and we have frequencies and wave numbers, we can let it run longer than just this 1.2 seconds. And if I let it run for 10 times as long, now you see some clear wave motions, right? And you see how the waves become shorter and slower and they turn towards the coast. Of course, if you have been in my wave course, you know that that's what they should do when it gets shallower. And here you have an example of an observation that shows that it really is like that. Okay, that was the depth retrieval. Now we are also working on current retrievals, which are more complicated because now you need to retrieve vector currents. This is an image from last year. This is even 25 seconds. This is from ICE-ICE and from the little 70 kilogram Finnish satellite. At Tinian, Mariana Islands, I think Gabi and Maddie were there, right? For while this took place, when you were on the ship. And we got this from ICE-ICE, and Hans asked me if I could process it to see if I can retrieve the currents. And here you see when I reduce the bandwidth, you begin to see the waves. And then you see, when we do this time series, you see a lot of wave motion there. You see two wave systems moving. Can you see that? You see waves moving this way, and you can see waves moving that way. And that should be all you need to retrieve currents, because now you have two components. You can look at their Doppler shifts, because they are advected with the currents, and you can retrieve current vectors. And that's still unfinished. I thought I could show you a current field today, but I didn't have a really good looking figure. So this is the end for now, but it's coming. The problem here is you cannot do a full Fourier transform in time. You have 25 seconds, but that's still not enough to do a Fourier transform in time. So you only have mean frequencies for every Fourier component and not a full frequency spectrum. And that makes the whole filtering process a little more tricky and challenging. But I think we have figured it out. Just need a little more time. Okay, now to this recent project here, the NOP Hurricane Coastal Impacts project. That's our website. So the project goal, nobody can read this, but it says, this project we aim to enable better understanding and predictive ability of hurricane impacts to serve and protect coastal communities. And the approach is to tackle blah, blah, blah. We have 10 teams, in fact, even more than 10, so 10 main teams, but with additional government partners and industry partners, altogether more than 20 organizations working on this for 4 years. Several millions of dollars were spent, and experiments were done, and modeling, a lot of modeling was done, and we acquired images. And if you want to see more about this, there's a website, even with the QR code here. And was exciting. We got an award for this project last year, the NOP Excellence in Partnering Award. NOP is the National Oceanographic Partnership Program, and our team got this award. I think we were the best, the most exciting project last year, and we are still working here with Hannah and Diana on a little kind of release on Facebook or so about our award that we got for the project, and we will show a little bit what we have done here with the satellite data. So our task obviously was to conduct the remote sensing, focusing now more on the land. We have sea stars, of course, involved in this. You see a picture of sea stars. And our industry partner was Airbus Defence and Space in Germany, who have these Terracer X satellites. Some wind retrieval examples here from Mike Caruso. This was not the core activity we had to do, but just to show you that this is possible. Here's a SAR image of Hurricane Lee in 2023, and the wind field he retrieved, and this is for comparison a model result from COAMS. And here, when you look at the upper left figure, you see there are several locations here. Those are additional locations where we had images. And so there are, again, the retrieved wind fields and the model wind fields. And the agreement is not perfect, but it's good. And there's our own hurricane hunter, Victoria Pizzini, who had an opportunity to fly with the Hurricane Hunter airplane, right? Not into this hurricane, but into some other hurricane. And she is working on these wind fields very much, right? Comparing wind fields from the SAR and from some other instruments, also from the NOAA people, some stuff that is outside of our NOP project. So a bunch of different data sources that provide wind measurements, and Victoria is comparing all these wind data. Here's another example here. This is from Mike Caruso of Sea Stars. I think he is in our Zoom meeting as well. You see a SAR-derived water line there in red, based on the contrast between land and water during the hurricane, and the so-called national coastline, which is the official coastline in green. So you see the waterline was higher and more inland. And there's the Google Earth background, and you can see the flooded area there in yellow. That was done by Mike. And then what I did was more focused on topography over land, and the challenge here was to get land topography, to get building heights and see if buildings get demolished by the hurricane, but also to get the land topography for flood predictions and so on before the hurricane comes, to get the latest updated topography. And the idea to do it quickly was to do radar grammetry, which is like stereo photography with a radar. So you have to take two radar images with different incidence angles. And here, this was Hurricane Ian. We thought it would hit St. Petersburg. That's why we acquired the images there. Before and after the landfall, unfortunately, the main landfall was a little further south. It didn't really do much in St. Petersburg, but we still used these two image pairs to test the radar grammetry. And here is zoom into St. Petersburg. This is the radar grammetry height product that our friends at Airbus got from an existing radar grammetry algorithm. These are reference heights from NOAA, from a LiDAR data set obtained from LiDAR flights with an airplane. There are no buildings here. This is just a terrain model. In our product here we still have the buildings, not very well resolved, but there are some noise from buildings. If you filter that out, you can get a little better. Here's another product from the second image pair. And when you do the statistical analysis, you see pretty good agreement with the reference data in the first case and in the second case, and between the two cases. So that's an example of radar grammetry. Then, last year they told us they have something even better that can resolve individual buildings better. This is a new building height product based on something developed at the German university by this guy, Michael Reckler, who's a PhD student, and his professor, Michael Schmidt. Here you look from two opposite directions, and then you use a machine learning technique. And you exploit the shadows of the buildings in SAR images. I will show you in a moment. And this is not good for measuring the total topography. The digital terrain model has to come from somewhere else, but you can measure the building heights. And we tested that again here at St. Petersburg, took new images just for this test last year. This is a Google Earth background. This is not our image. This is one of our images. And this is another image looking from the opposite side. Now focus on that area there. You see the buildings in the SAR image, and there they are in Google Earth. And now if you look at the other image, and you fade between the two images, you see that where there is a building, where something is sticking out very much, it's moving very much between the two images. And where you have road surfaces or these tennis courts, here they are not moving because they are close to the reference ground level. And from these motions between the two images, the machine learning system derives building heights. And here are the derived building heights. Pretty clean product. The shapes of the buildings are coming out very well. Much better than you would get from regular radar grammetry and also from radar interferometry, which would be another established technique that was too slow for this project. Here we wanted something that can be done very quickly. And we have another image pair in different imaging mode that gave almost the same result there. So that's what we did here. See the buildings are at the right place. The height seems to be correct. I haven't analyzed this completely, but I will do that in the next few weeks because this project is formally over. And the latest thing we did, because we still had some money and we wanted to test a little more at a new place, we went to San Francisco, which has elevations already up to 300 meters or so. So these are just the hills here in the colors that you see, but you also see the individual buildings. If you zoom in, you see here the isolines are every 5 meters, I think, or every 10 meters. No, I think every 10 meters I have an isoline. And you see, when you look carefully, you can see the isolines of the hills, and you can see the shapes of the buildings, and this looks quite good. another case that I still need to compare with the LiDAR data, but we have 4 different couples of images that are very consistent with each other, and I think this will also be consistent with the LiDAR. The only thing it cannot do well is very tall buildings. When the buildings are too tall, and there are other tall neighbor buildings around, there is too much overlap between those signatures, and it doesn't work anymore. So that's that, and we are getting to the end of the presentation. So I made it almost on time. So this has hopefully given you some idea of what I'm doing and what are the main achievements from the last 30, 40 years, also from the last few years with these latest projects. And so there was a numerical SAR and a long-track INSAR simulator on which I worked for a long time, and that many other people in the world got to use. By the way, I gave them executables to run this on their own computers. We did some world first a long-track INSAR test with the space shuttle, the XR, and then with TerraSAR X and Tandem X, all thanks to Hartmut Runge, who helped me to get the data. We developed SAR image reprocessing tools, a lot more than this one that I showed you for the ghost signatures. That was just one example. We got into the sub-aperture image processing for wave, depth, and current retrievals. And in the latest project, we tested the land topography and building height retrievals. And that's it. And I wanted to emphasize here at the end that this is really more remote sensing science and engineering than ocean science, and that's why it has always been a little challenging for us to find good students who wanted to do this kind of thing. Most students who come here want to be ocean scientists, they want to study the ocean. And the people who want to do this are probably more looking at the engineering department or so, although they should work with us on this stuff. So maybe they can watch these videos, this video here and these slides, and see that this is interesting stuff that they could do, but they will probably say they don't want a degree in ocean sciences. So that's one thing we should perhaps work on, if we can have students here who are our students, but they can get a degree in engineering. That's my message for the future, my hope for the future. So that's all. Thank you. I hope. You liked it.
Thank you, Roland. Do we have any questions in the audience? All right, I thought Dave first.
So Roland, as I'm sure you know, in the hurricane business, people are very excited about SAR now, and it seems like there's just more and more and more SAR images of hurricanes, and they look amazing. But I guess there's still some uncertainty and controversy about the accuracy of those images or the wind speeds, right? And I remember from Victoria's presentation that there was a lot of uncertainty raised there. So what would you say is the state of our understanding of how accurate these SAR images of hurricane wind speeds are?
Yeah, we just had a discussion about this with someone in our project team last week, because we had sent him a few wind fields. Yeah, there are still some discrepancies. We have a case, Victoria could perhaps answer this better than me, but we have one case where we have 3 images from 3 C-band satellites right over Hurricane Helene, right? From 2024, so the same area, almost the same time, within 2 minutes, 3 images, and 3 wind products made with basically the same algorithm with slightly different coefficients for the 3 satellites. The wind fields are quite similar. When I look at them, I think that looks quite good, but the modeling people say, oh, why is it different and what's going on? Which is the best one? So yeah, there are some variations, there are some calibration issues, some tuning issues perhaps of the model functions. So yeah, it's not perfect, but this is a good way to get a high resolution wind field, and you really can look at the surface. You are not just looking at moving clouds or something like that. It should be used together with other data that you can get, and if you can get this in addition to the other things you have, and you can combine it with models. Here what I showed, I didn't talk too much about it, but what Mike Caruso did there was not just a simple SAR product where he had just converted the intensities into winds, but he has already applied a boundary layer model that applies some physics to the wind field and corrects it and makes it more consistent with what you would expect physically. It makes a surface level pressure field, and then it somehow goes back from the surface level pressure field to the wind field. And that smooths it out, and there are some artifacts and some inconsistencies in the shape of the wind field and so on. This technique smooths it out, and it looks to me as if it's not too bad. How useful it really is, that should be answered by the people who want to use it. But I think it has improved quite a bit over the last 20 years or so that we have done this with SAR. Initially, wind measurements from space were more done with the sketcherometers, which still exist, but they have a much lower resolution, right? They cannot resolve the hurricane survey. Here you have high resolution. You have basically the same technique that the sketcherometer uses, but with a higher resolution, and I think it's not too bad. Again, this was not the main focus of this project, so we were not really required to deliver very good wind fields, but we did that anyway, and we can now analyze how good and how useful they are. And Victoria will analyze it even more with her friends at NOAA.
Yeah, Roland, my question is similar to Dave's, but for climate, you have like 20 or 30 years of these things flying out in space. How much of that data is suitable for looking at long-term trends and long-term changes? How stable is it? Calibration accuracy, that kind of thing?
So the calibration is usually pretty good and consistent. One issue could be when you have a time-limited SAR mission and the next mission is different in its technical parameters, using a different frequency, using a different resolution, and so on. Then it's difficult to compare the products and to apply the same algorithms. But we have, for example, the Sentinel-1 program now of the European Union. They have typically 2 SAR satellites that take images quite operationally according to a fixed plan, and they cover all the coastal areas and some land areas, and they can also be turned on when there's a hurricane. And that will go over many years with new satellites that continue the mission with the same properties. And that would be a good time series for studying long-time trends, right? And you could apply the latest algorithms to the old data and see what you...
Are there any products being developed like that, or is that not being done
some
yet?
specific products for long-time trend analyses? I don't know. I'm not, as you see, I'm not so much in using this. I'm more into developing it, and when it works, I develop the next thing. So I don't know. I'm not a long-term user of the same product, but of course one idea behind Sentinel-1 is that there is a continuity, and you have the same kinds of products over many years.
Thank you, Roland. This is definitely worthy of 2 chocolate bunnies, if that's possible. So your last kind of topic with the building topography and height used a deep learning technique. Do you see any other big advances coming from AI or other kind of models like that in the near future with your field?
You are asking the wrong guy. I think... So maybe I'm too old-fashioned, but I think AI is a little overhyped in this field. People are trying to apply AI to problems where it would make more sense to use your understanding of the physics and develop a traditional algorithm. Something like this with the building heights makes sense because that's a little bit like machine vision. You see there's something going on with the shadows of the buildings. That would be difficult to translate into equations and code that will do computations to simulate what your brain can do when you look at how the building moves around between the 2 images, you have a feeling for how tall it is, right? You see where the tall building is and not so tall building, and so your brain can make sense of it. It would be very difficult for a human to translate that into some algorithm that computes the building height. And that's something that the AI can do better, I believe. The AI can just look at so many examples that it can figure out how to estimate the building height. So that's good. So for these things, it's good. For some other things, I think it's still more useful to use traditional algorithms and to take my remote sensing courses to learn how the imaging mechanisms work. And then if you see some artifacts in an image or you see some features in an image, you can understand why these things look the way they look and what you would have to do to retrieve the kind of information you want to retrieve.
Well, I don't have a question. Thank you for today's talk, but I think we also need to thank Roland for running this whole Compass series and for doing it so well. So Roland deserves a round of applause for this.
Yeah, thank you, and again, thank you all for coming. And it's good to see that at least for my presentation, I could mobilize everybody. I hope this will not be a single event. Maybe you see now that it can be really nice to be here. It will come again in the next few weeks. So next week, Alex Soloviev will speak. There he is, from Nova Southeastern University. And in 2 weeks, Joe Prospero, our emeritus professor, another very special presentation. And I don't remember what comes after that, but we have some really great stuff coming up, and I hope to see most of you again for that.
Great, thank you all.